Good day. I'm Norman Walberger, and today we're going to introduce rotations into our framework for basic geometry. And we're going to do so entirely in the realm of the rational numbers, which is the proper and best domain for thinking about geometry. So, intuitively, a rotation is something that we're all very familiar with. You get a piece of paper and you rotate, turn it around like this. But what we want to do is we want to peg that down precisely in terms of mathematical concepts. So here's an example of a rotation about this point A. We're working in the grid plane. So there's a rotation that moves the line M to the line M prime. It fixes the point A. This point B is sent to B prime. This point C is sent to C prime. This point D is sent to D prime. A little circle like this would be rotated around to another circle like that. So intuitively, we have a very good idea what it means. How do we proceed formally? The usual framework says that we should start by thinking about a function from the plane to the plane, the real plane to the real plane. And then there's some physical description in terms of somehow describing what this turn or rotation does. Often the angle is used to describe how much we are rotating by. There's plenty that's wrong with this approach. First of all, we don't believe in the real number plane because the real numbers have not been established yet. We don't believe in infinite sets. And the notion of angle is very problematic, as the ancient Greeks, even Euclid, realized quite well. It takes a lot of work involving calculus to talk about angles correctly. And since we're interested in concepts which are only completely correct, we're not going to use angle. So to simplify the situation, what we're going to do is we're going to look not on what rotations do to points, but rather what they do to vectors. So for example, the vector BC, which is the ordered pair BC here, that little green vector there, when we rotate B to B prime and C to C prime, this vector here, call it V, is rotated to this vector V prime. And if you take any other vector which is a translate of V, so still the same vector V, then it's also going to be rotated to a vector parallel to V prime. So rotations act on vectors, and it turns out to be much simpler if we concentrate on rotations acting on vectors. So I have to remind you that vectors and points, although they're closely related, they are different objects. And so what we're going to have to do now is turn our attention from the grid plane involving points to the vector plane involving vectors. All right, so let's have a look at this vector plane. It's a lot like the grid plane, but it's describing vectors, not points. So this position here describes the vector emanating from the origin to that position. 1, 0 corresponds to this vector. 0, 1 corresponds to this vector. And what we're interested in is describing a rotation. So here's the unit circle. Things have been expanded a little bit from usual, so we can see this a little bit better. And we're assuming we have a rotation that sends 1, 0 to some point AB on this circle. So that's the rotation that we're interested in. Then this vector 0, 1 is going to be rotated to a vector which is perpendicular to this one. Perpendicular to AB minus BA. Those two vectors are perpendicular. So we've got a rotation that takes these two vectors and sends them to those two vectors. And what does it do to a general vector, say like this one xy? Well, we use the linearity of the rotation. The fact that since this vector is 2 times this one plus this one, so 2 times this one plus that one, then when we rotate it, we're going to get 2 times this vector plus this vector. In other words, up here. Okay. This is also the key for understanding this rotation algebraically. We've assumed that 1, 0 goes to some vector AB on the unit circle. 0, 1 goes to minus BA, which is perpendicular to AB. Then a general vector xy, which is x times 1, 0 plus y times 0, 1. So it's a combination of the two basis vectors. that's going to be sent to the corresponding combination of AB and minus BA. So it's going to be sent to x prime y prime, which is x times AB plus y times minus BA, because this vector is sent to that one and this one's sent to that one. And we just work this out coordinate-wise. The first coordinate is a times x minus b times y, and the second coordinate is b times x plus a times y. And this then gives us a formula for what the rotation ought to do. The rotation should send xy to this vector. And this now is how we can define what a rotation is. We say that a rotation is just this symbol, rho with an AB, because it's determined by that vector AB on the unit circle. And it's a symbol or an expression that has the following interaction with a vector. If you have a vector followed by our symbol for our rotation, then that combination is by definition this new vector. So we define the rotation by how it acts on the expression of vectors to yield another vector. We get a new mathematical object, which we might call a vector rotation, or v-rot for short. And this is how we're going to think about what a rotation is. Now let's say a few words about how we combine rotations and how we can think about AB on the unit circle more precisely. So let me remind you that if AB is a point on the unit circle, x squared plus y squared equals 1, then we've shown before in our video on parametrizing the circle that AB is either the point minus 1, 0, which is on the x-axis on the left-hand side, or it's given by this particular beautiful formula involving Pythagorean triples. 1 minus t squared over 1 plus t squared, 2t over 1 plus t squared. For any value of t, for any rational number t, this defines a point on the circle, and every point on the circle is of this form unless it's this one here. So let's introduce a shorthand for this. Let's say that this vector, we'll write it now as v sub t. So our rotation by this vector AB, which we usually called rho AB before, we can now write rho sub vt. Okay? It's the rotation that sends 1, 0 to this particular point on the unit circle. Okay, so now here's a very interesting and important exercise that really says a lot about the structure of rotations. Okay. If you have a vector xy and you apply rotation by this vector vt for some t, and then to that you apply another rotation vu, so you take another point now with t replaced by u, then that combination, one rotation followed by another rotation, can be written as xy times a single rotation, vw, where this w depends on t and u in this relatively simple form. W equals t plus u divided by 1 minus the product t times u. Now this is different from angles. If we were rotating with angles, we would just be adding. We are not using angles because angles are way too complicated. But with this rational formulation, this formula replaces the ordinary addition of angles. It's a very important formula, not nearly as well understood and used as it ought to be. So it's a very interesting exercise to do that. And then we can introduce this notation that will just now say that rho of Vt times rho of Vu, this expression, it can be replaced by rho of Vw, where this W is given like this. We're going to say more about rotations. This is just sort of the first starting point. But on our next video, we're going to now turn to reflections. If you've understood what we've done for rotations, then understanding what happens for reflections is not very difficult. It's much the same. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.